I'll try, again, I'm going to try recording today's class session. Hopefully it doesn't cut out on me. So, Nathaniel, Alend, Nathaniel again, Abel, Yard, Scott, Kennedy, Missy, Amanda, Chloe, Sally, Josh, Sergey, Josh, 17. Ollie, Ivan, Nathan, not here, Reese, Missy, Josh, Salvador here. Okay. So I want to make sure I get through this marginal analysis section. Let me get the door shut first. Okay, so let everybody kind of know the schedule then for the next week. It's unfortunate the way the scheduling worked, but the exam I'm going to have on Monday. Friday's going to be a review day. I'll try and come in again this weekend if anybody has any times they can make it in. What would really generally work better on weekends for people? The building is open from 9 to 5. So, is there anybody that's busy that whole time? 9 a.m. to 5 p.m.? Okay, so those people are out. Would before noon, who can maybe make a session before noon? Nobody? Is there anybody that couldn't make it in before noon on Saturday? Okay, how about afternoon?
I get off around 2.
You get off around 2? Okay, so what would, say, 2 to 5 p.m.? I don't know if everybody can make that stretch. Okay, so I'll be in this room on Saturday, 2 to, maybe 4 p.m. at the earliest, but maybe we'll see. I might be able to stick around till 5. Okay, so what we'll do is we'll review on Thursday. What's it, Tuesday today? So Wednesday, Thursday, I'll finish up 3.1 and 3.2. Those two sections are going to involve exponentials, so we'll talk about some exponential models like compound interest and other things that involve exponentials. And we'll just talk about derivatives of exponentials as much as we can. I'm going to postpone the derivatives of logarithms until we need it. If it turns out we don't need derivatives of logarithms, I might skip it altogether. So the only thing really left to cover the next couple days is just a little bit about exponentials and derivatives of exponentials. Okay, and so basically 3.2 is what we're going to get through. So 3.1 I'll cover pretty quickly because it's a review of algebra essentially. And then 3.2 is probably back into the calculus finding derivatives of exponential functions. Okay. So we did an example yesterday and kind of led up to this point. Now I'm going to start at the top of page 2. Before I write this theorem down, I want to kind of remind everybody of what we've done now. So one thing we know for sure is that, let me see here, if you want to use marginal analysis, we've done problems where, if you say the cost of producing X items and the marginal cost of producing X items. We've used this fact that the cost in producing the X plus first is approximately the same as the cost of producing the previous X items plus the rate of change of producing those X items. Okay, so we've used this fact before. I think on the homework I just turned back, you've used this fact. Okay, so one thing I can do here is I can actually solve for, let me make sure I'm not screwing this up. Sometimes I write things down wrong. Let me get my notes here. Where did I have come on. Oh, there it is. So what I can do here is I can solve for C prime of x. So if the cost of producing the next item is approximately the cost of producing the previous x items plus the marginal cost, okay, or sorry, the cost of producing all x plus 1 items is the cost of producing the first x plus the derivative there. C prime of x is going to be approximately the cost of producing the x plus first minus the cost of producing the first x items. Okay, and what we have on the right, this is the exact cost of producing just the x plus first unit. Okay, and this right here is the approximation. Okay, so if I want to approximate the cost of just producing that single x plus first item, I can just take the marginal cost of producing the first x items. Okay, or what the rate of change is if I've produced x items. Okay, and this is basically what the theorem says. So the theorem on the top of page 2 says if C of x, R of x, and P of x are cost, revenue, and profit of producing x items, then you have a similar one. I just wrote this one down. So the right-hand side is the exact cost of producing the x plus first. The derivative at x is going to approximate that value. And you can also do the same thing with revenue. So I'll write this down. This is the exact revenue generated in selling the x plus first unit. All right, if I take the revenue from selling all x plus 1 units and I subtract the revenue of selling the previous x units, you're left with just the revenue generated by selling that single x plus first unit. Okay, and then there's also one for profit. You can use the marginal profit to approximate the profit generated in selling the x plus first item. Okay. And using these facts is what we call marginal analysis in business. Okay. So we've essentially kind of already used these formulas before in a different way, but resolving for the derivative in each of these formulas, that's a way to approximate the exact cost of producing an additional unit when you've already produced x units. Okay, so back to, I think, same example as before. So example 2. See if I'm still recording. Yay! Okay. So remember, if we're selling X remote controlled drones per week, the cost in selling X remote controlled drones in a week is 10,000 plus 700X, and the revenue generated in selling X remote controlled drones is 1,000X minus the, I'm going to write it this way, 1 over 20,000 x squared instead of x squared over 20,000. And again, suppose this manufacturer has the ability to produce up to 1,000 of these drones per week. So that's their window of production, if you like. They can produce anywhere between no drones or 1,000 drones. Okay. Part A says find the exact profit in selling the 601st drone. So that's going to be calculating the right-hand side of this expression. Part B says use the marginal profit to approximate the profit in selling the 601st. That would be using the left-hand side. So part A, if I want the exact profit in selling just the 601st drone itself, so you're assuming you've already produced the first 600. what would be the additional profit in selling one more. Okay, so that would be the profit of selling all 601 first drones, and then you subtract the profit generated in selling the first 600. And that would give you the profit gained just from selling the 601st. Okay. Now, we'll figure out what this equals. Now, I wrote this down yesterday because I think we've been using the same example now for the last like 3 problems. The profit ended up being revenue minus cost. I think we got 300x minus 1 over 20,000 x squared minus 10,000. I think if I take my revenue minus my cost, we'll end up with this profit function. Now I'm going to try and get as many decimal places as I can. So maybe I'll round these to 4. We'll see what it ends up being. So plug 601 into this function. I get $170,281.94. Okay. So if this manufacturer produces and sells 601 drones, their profit there would be 170,000, just over. And then let's see what their profit was in selling the first 600. I get a whole number for that. I get $169,982. Let me rewrite this a little bit so I have some room. And this ends up equaling
299.
What'd you get? 299?
299.94.
Okay. So that's just telling me that if I've already produced and sold 600 drones, to produce and sell the 601st, that 601st one will yield a profit of $299.94. Okay. So you actually do obtain a profit. Okay. Now what we're going to do in part B is we're going to use the derivative at 600, the marginal profit, to approximate this, the exact profit in selling the 601st. And if this theorem is correct, that approximation should be really close to this exact profit. It's on the ground. Okay, so part B says approximate the exact profit in selling the 601st drone. So what we're going to need there is we want to find the marginal profit when 600 units are produced and sold. So we have to find the derivative p prime of x, our marginal profit function. And I think we already did this yesterday too. It's going to be 300. So the derivative of 300x, think of the derivative as just the slope of the line 300x, which is 300. And then the derivative of the next term is going to be minus the constant 1 over 20,000 times the derivative of x squared, which is 2x. If you simplify, you get 300 minus x over 10,000. So I'm moving this 2x into the numerator, and 2 divided by 20,000 is 1 over 10,000. And then Ollie, did you chug this already?
Oh, do I have to plug X in already?
Yeah, I don't know if you plugged this in yet. I saw you had your calculator, but we can all do it. So 300 minus the 600 over 10,000.
299.94.
And I get exactly the same thing that I had before. I think this happened yesterday too. Now, this isn't always going to happen. This was just a fluke. It happened by chance. It's not always going to be the case that the marginal profit is exactly the exact profit. Okay, so certainly on your homework you'll find times where this value is going to be different than this, but they're going to be very close to each other. Okay?
Yeah, I saw that.
Yeah. Okay. All right. So that's pretty interesting. I guess all this is really saying is the slope of the secant line is the same as the slope of the tangent line at 600, just by fluke. Okay, but not in general. There's going to be times where they'll be different. Okay. So any questions there? Again, we're just using the same fact that if you want to find the profit in selling the x plus first, it's the profit of selling the first x units plus the derivative at x. And then if you solve for marginal profit, marginal cost, marginal revenue, again, this right-hand side, that's the exact profit in selling the x plus first unit. P prime of x is the approximation to that profit in selling the x plus first unit. Okay. In this case, they're both the same, but that won't happen in general. Okay. So any questions there? Maybe just about the idea that's going on? Yeah?
For B, did you actually want to find the 600 or the 601?
So it's this formula right here. So notice how it's x plus 1 and x on the right, but it's just x on the left. So this would have been 601 and 600, so I plug 600 into the derivative. If that's the rate of change in selling x units. Okay, so that means if I sell an additional unit, our profit increases by about p prime of x. Okay, so if we already produced x units, p prime of x is approximately the profit in selling one more. Okay. So yes, it was supposed to be p prime of 600 for the approximate, and then the exact value of selling just the 601st is this quantity.
And it's not always going to be the same.
It will not always be the same. Okay. So again, this exact value, when you approximate it with the derivative, this usually ends up being different, but very close. Okay. Maybe what I should do in the future is construct an example where they are different. Okay. So just make sure you pay attention. It's really an approximate symbol. So sometimes, just depending on the numbers you choose, they might be the same, but most of the time, or in general, your approximation will be different than the exact value. Okay, so let's see. I got another example. Example 3. How are we doing on time? I got 27 minutes. Video is still recording. Okay. So now I want to do an example with a price-demand function in revenue. Now you've seen some of these maybe on the homework pop up. There was certainly a homework problem that I forgot to do yesterday. What was that problem you asked about?
92.
It was like 92, and then I forgot to do it. But if anybody wants to, I can stick around for 5 minutes and go over that after class. Or if I get done fast enough, I'll just do it real quick at the end. Okay. So example 3. Keep those approximation formulas in mind again. So suppose the number of units demanded X of a particular good can be written in terms of the price per unit P as, so the number of goods demanded is 5,000 minus 500 P. So P is the price per unit. I'll write this down. X is number of units demanded. And P is the price per unit. Now, what do you know about demand as price increases in general? So, and this doesn't happen for all goods, actually. There's certain kind of things, I forget the names of them, we'll get to them later in the text, but certainly luxury items are kind of weird. Like Lamborghinis, sometimes as the price increases, the demand actually increases because it's a luxury item. The more expensive it is, the more we want it. Okay, but for most goods, the number of units demanded are going to decrease when the price increases. Or sorry, decrease if you increase the price. Right? So because we're subtracting minus 500p, if we increase the price, it's going to reduce the number of units demanded. Okay, and that's true for most goods. Okay. Certainly gasoline might be one of them. I'm not really sure. That might be one that's more stable, where the price changes don't really affect the demand. Okay, so we'll get into that more later. So in general, though, the number of units demanded will decrease as price increases. Part A, I won't write it down. It just says, write the price per unit as a function of the number of units produced, P of X, and find the domain. Okay. So we're trying to find a function P of X. Now, I guess I can talk about 92 on the homework. That question is just saying find the rate of change in units demanded with respect to price. That problem, you're just supposed to take the derivative treating P as the independent variable. So, in a sense, P is really the X, and the X is really the output Y. Okay, so when you do that problem, you're just taking the derivative of the right-hand side, the expression involving P. Okay. Whenever they say with respect to a variable, that's the independent variable. That's what you're treating as the X. Now, if I want to do this, all I need to do now is solve for P. So one thing I can do first is I can add 500p to the left and subtract x to the right. So I did two things there. I added 500p to both sides, and then I subtracted x on both sides. And then if I want to get a function p as a function of x, now I just divide both sides by 500. And I think you'll get 10 minus 1 over 500 times x.
On the homework, they made us put that into decimal.
Okay. Off the top of my head,
It's 0.002.
0.002. Okay. I personally don't care as much if it's a decimal or a fraction until you actually like plug something into this function. Then you'd maybe want to give it as a decimal number, but personally, it doesn't make as much of a difference to me. But we'll stay consistent with what the textbook is doing. Okay, so I just solved for p, and then since I solved for p and it depends on x, I can write p as a function of x. And then it says find the domain. Alright, so if I want to find the domain, we need to use two facts. Can the number of units demanded ever be negative? Would that really make much sense? And can the price ever be negative? That wouldn't make much sense either. So the domain is going to come from both of these functions. Okay. So first of all, looking at the price as a function of units demanded. Okay. So I'm trying to find the domain now. So finding the domain of P. So first observation. So first we need the price to be greater than 0. So now we have to solve an inequality. Okay, so I need the function p of x to be positive. We need to find the x values that make that true. So I just need to know where the function, so replace p of x with the equation of the function 10 minus 0.002x and set that greater than 0. And then now, well, solve for x. So I can add the 0.002x to the right-hand side. 10 is going to be greater than 0.002x. And then just divide both sides by 0.002. When you do that, I'm going to switch the inequality the other direction. But what's 10 I guess I could just say 10 times 500. I think that we're going to get 5,000 on the right. Okay. So again, I added this term to the right, divided by 0.002 on both sides, and then I just switched the direction of the inequality. Huh?
I thought it was only when you divide by a negative.
I didn't switch the sign. I switched the I flipped the inequality. But yes, Chloe brought up a good point. If you're ever solving these and you divide by a negative, then the direction of the sign will change. But I didn't change the direction of the sign. It's still opening away from x. Okay, so down here it's still opening away from x. Okay, but that's good to point out. So now that just means that the number of units demanded is always going to be less than 5,000. Okay. And then looking at this expression up here, let's see. Well, I guess we can just finish this. The number of units demanded on the one hand is less than 5,000, but it also has to be positive. So it has to be greater than 0. So the domain now is equal to the set of all x such that basically we're just saying the number of units produced has to be between 0 and 5,000. So that's the domain of the price function. So that's part A. We found p of x and we found its domain. We just denoted that if x is the number of units demanded, for free we get that it has to be greater than 0. And then to figure out the upper bound for the number of units produced, I set the profit or the price function greater than 0 and solve that inequality. So this only makes sense if the number of units demanded, which generally you assume is the number of units produced, is between 0 and 5,000. Okay, now part B. So first of all, have we really done any calculus yet? No, we haven't done any limits, we haven't taken any derivatives, so we're still working with algebra. We won't get into any calculus till part C. Okay. Now part B says find the revenue R of x, where x is the number of units sold or produced. Okay. Now revenue, in general, revenue is usually just how much money is coming in. Okay. How much money are you generating? To find the profit, you'd have to subtract cost. But if you have a price function like this, the revenue R of x is always the number of units times the price per unit. So number of units sold times price per unit. How many people have seen that fact before? Okay. Right, we're just taking the revenue of selling X units. You just take the price per unit times the number of units that you're going to sell. Okay. So if you come up here, X was already given as the number of units demanded / sold. So that's going to be the first term up here, X, and then you're going to multiply that by the price per unit. That's what part A was about. The price per unit is depending on the number of units demanded. Okay, so the price per unit when X units are demanded is given by this linear function right here. That becomes the second factor. So it's the number of units X times the price function. And the revenue becomes 10x minus 0.002x squared. Okay. And the revenue function always has the same domain as the price function. I didn't ask for that, but we're going to use the same domain for the revenue function as we did for the price function. Okay, everybody okay so far? Don't want to get too far ahead of myself. And then finally part C says It says find the marginal revenue when 1,000 units are produced and use that to approximate the revenue in just selling the 1,000 first. Okay, so remember now, R prime of x is always approximately R of x plus 1 minus R of x. The right-hand side is the revenue generated by selling the x plus first unit. And we're going to use the left-hand side to approximate that. This is part C. So first of all, we have to find the revenue function, the marginal revenue, R prime of x. Sorry, we're way over on the board on the right. What's the derivative of the first term, 10x? Okay, that'll just be 10 minus, and then what's the derivative of the second term? When you bring that 2 down out front, your decimal becomes 0.004.
Oh, four.
Yeah, we're gonna use the power rule. The power comes out front and multiplies with the 0.002 to get 0.004, and then you're just left with x. But yeah, I see what you're saying. You were gonna say the 0.002 times the 2x. Okay. So I'm skipping a few steps here, but everybody okay there? Okay, so there's your marginal revenue function. And if I want to approximate the profit in selling the 600 approximate the revenue in selling the 600 first, I'd have a 601 here, but we actually plug 600 into the derivative. So R prime of 600 is approximately the revenue in selling the 601st unit. And let's go ahead and plug 600 into the marginal revenue function.
Doesn't C ask for 1,000?
Does C ask for 1,000? Oh, am I being silly? Where am I getting 601 from? Previous example. My bad. I broke the golden rule. I didn't read the directions. So sorry, the question is asking you to approximate the profit or the revenue in selling the 1,000 first unit. So you evaluate the marginal revenue function at the previous unit of number of units, which is 1,000. And again, remember all this is saying? This is just saying if we've already produced 1,000 units, R prime of 1,000 is approximately the revenue in selling an additional unit, i.e. the 1,000 first. So we're going to do, here I'll actually plug it in this time. Sometimes I skip this part, but I'll write it in. Now what does multiplying something by 1,000 do to a decimal? Well, there's 1, 2, 3 zeros. The decimal goes to the right 1, 2, 3 places. So this is 10 minus 4, which equals $6. So if we've already sold 1,000 units, selling one more is going to bring us in an extra $6, approximately. If I wanted the exact value, I could do R of 1,001 minus R of 1,000. Maybe this time it would actually be different. I could check to see what how much I have to do in the next example. I'll leave that for y'all to investigate if you want. Okay, so that's the approximate to the revenue of selling the 1,000 first. You'd have to take R of 1,001 minus R of 1,000 to get the exact revenue generated. Okay. So next thing we're going to do is just talk average cost and marginal average cost. Okay, so same idea, it's just we're going to first find all the average functions. Okay, so you can find the average cost and the marginal average cost, and you can do the same for revenue or profit. So the next one, there's a definition. If you're looking at cost per unit. So if you have a cost function, the average cost is the average cost per unit if X units are produced. Right? Each unit might have a different cost associated with it, but when you take your cost function and divide by the number of units produced, that tells you the approximate cost of just producing each individual unit. And there, the average cost function is defined to be your cost function divided by the number of units produced. Okay. And then you've got the marginal average cost. I'm just going to write this one down. The same definitions are true for revenue and profit. So the marginal average cost function is equal to, it's C bar prime of X. So that's the derivative of the average cost function. And it's defined to be the derivative with respect to X of C of X over X. I gave you one additional step. Actually, let me write this down. So here's what, it's the derivative of the average cost function. Another way of writing that is the derivative of the cost function divided by X. Okay. So these are just two notations. Saying the derivative of the average cost is the same as derivative with respect to the independent variable X of the average cost function. Those are just two notations for the same thing. Okay, and then the same holds for, you have similar definitions for average revenue and average profit. Okay, so example 4. We have time almost. Okay, so again, back to that example of selling X remote-controlled drones. The cost of producing X remote-controlled drones was 10,000 plus 700X. If I produce 100 drones, I plug it into that function. That gives me the cost of producing those 100 drones. And then we're going to find in part A, we're going to find the average cost function, so C bar of X. Have a good number of you taken statistics before at all?
Yeah.
Okay, so you know when you take a variable and put the bar on it, that's this notation for the average. Okay. And that's just obtained by taking the original cost function and dividing by the number of units produced. And I'm just going to divide both of these terms by X. 10,000, I'm going to get 10,000 divided by X plus 700X divided by X is just 700. So this equals, I'm going to write it this way because we're going to have to take a derivative in a second. So dividing by X is the same as multiplying by X to the minus 1 power. So the marginal average cost, that gives you the rate at which the average cost is changing, okay, when X units are produced. This is just going to be the derivative of our average cost function. The derivative of a constant is always 0. Limits of constants are the constant, but derivatives of a constant are 0. So you only need the derivative of the first term. You're going to bring the negative 1 power up front and reduce the power by 1. So I should have minus 10,000 x to the next lowest power of negative 2. And if you like, that's negative 10,000 over x squared. So there's part A. The average cost function, just divide the cost function by x and simplify, and then take the derivative of that to get the marginal average cost. Part B says find the average cost per unit when 400 units are produced, and we're also going to find the marginal average cost in producing 400 units, which is the derivative. So the first one, we're going to do, I'm going to do it this way. I'm going to take 10,000. Instead of multiplying by x to the minus 1, we'll divide by the input x of 400, and then add 700. And let's see, 10 fourths is, actually 100 fourths is 50 halves. I believe that's just 25. So 10,000 over 400, someone might want to double check. But I think this is just 25, so we get 725 dollars per unit. So if you produce 400 units, that means that it costs about $725 to produce each of those units. We are still just on average cost.
Oh, okay.
The square doesn't come in until I take its derivative.
Oh, okay.
Yep. Video is still recording. Oh, it's over here. Okay, good. Okay, now the marginal average cost, which tells you how much the average cost is going to increase when 400 units are produced. This is going to be your minus 10,000 divided by 400 squared.
Which is negative 0.0625.
And that's exactly?
Yeah.
Okay. Now this is going to be weird. Because what are the units? Well, first of all, the units on the average cost are dollars per unit. Per unit. I know it's kind of weird. But remember, anytime you take a derivative, it's the units of the original function divided by number of units. So let me interpret this. This means when 400 units are produced, the average cost in dollars per unit decreases by $0.0625 per unit. It just says the average cost is going to decrease by 0.0625 per unit, which is actually good, because that means if I produce another unit, that means that the overall average cost will be decreasing. So that's probably good incentive to produce another unit, depending on what your revenue is. And then I only have a minute left, but part C, I'll kind of tell the story. So it says, find the marginal revenue when 1,000 units are produced. And, oh, how would I read the right question? It says, use the results from part B to estimate average cost per drone at a production level of 401 drones per week. So this is where I have to go back to the average cost of producing 401 drones per week. That's always approximately the same of the average cost of producing the first 400 plus the marginal average cost of producing 400.
So we just add 725.
Yep. we're going to take 725 plus the negative 0.0625. And then I don't know if that gives you, it's 724.9375 dollars per unit. So you produce one more unit, your average cost per unit goes down. Goes from about 725 of, that's your cost per unit if you produce 400, and then the cost of producing 401, the average cost per unit is slightly less than that. Okay. All right, that's all I got for today. Again, I can stick around, or if people have questions, I'll just go straight to the TLC if you like. This video session, or this class session, did record, so I'll get this posted on Canvas. I usually put these videos on YouTube. I have a YouTube page. I'll put the link to that video on Canvas under announcements.